Good evening, dear students, and welcome to my YouTube channel. This video is going to be a quick recap of gamma functions. So we are going to keep it very short, and we are going to see all the types and solve numericals. So you can take this as a practice just before your examination. So let us first start with the definition of the gamma function. The gamma function is defined as a consequence of the convergence of the improper integral given by integration from 0 to infinity e raised to negative x, x raised to n minus 1 dx. And this improper integral converges to gamma n. Please make a note that here the number n needs to be a positive real number. It's not necessarily to be a natural number. So this is the definition. Let us now see some properties of gamma function. So the very first property is the recursive property, and that helps us to evaluate higher values of gamma function. So gamma of n plus 1 can be expressed as n times gamma of n. Let me call this as P1, property 1. A corollary to property 1, if n happens to be a natural number. So in this case, by the earlier property, gamma of n plus 1 is going to be n times gamma of n, and this sequence will continue for gamma n, and as a result we can say that this is equal to the factorial of n. Thus, to cut it short, remember that gamma of n plus 1 can be evaluated as n factorial whenever n is a natural number. Let us see some standard values of gamma. Now, since it's a function of n, we are very interested in knowing like what is going to be the value of gamma n. So for example, if I tell you that we want to find out gamma of 3 by 2, so we should have a numerical value in our mind that gamma of 3 by 2 is equal to this. So if n is a positive integer, we have already seen. So if n belongs to set of naturals, then gamma of n plus 1 is evaluated as factorial of n. Or we can also say that gamma of n is equal to n minus 1 factorial. Thus, you can take an example quickly. So if suppose say n is equal to 8, then gamma of 8 is going to be 7 factorial, and we know how much 7 factorial is, giving us a value for gamma. Then for the second one, if the value of n is 0, so in this case, gamma of 0 is undefined, or it is going to be infinity. Again, if n is a negative integer, so that means n belongs to z minus, in this case also gamma of n is equal to infinity. Now for the fourth one is a very interesting property and you are going to use it very often, so I want you to pay a little attention over here. Now suppose say n is any fraction which is positive, so let's say n is a positive fraction. Then in this case, we are going to evaluate gamma 1 using property 1, which says that gamma of n plus 1 is equal to n times gamma of n. And you can just see that we could rewrite this for gamma of n. So gamma of n is going to be n minus 1 times gamma of n minus 1. So we implement this property and this is going to be looking like this, n minus 1 times gamma of n minus 1. Now again, we can apply the property to gamma of n minus 1. So the point over here is when do we stop? So we go on applying the recursive property, property 1, until the number n minus 1 inside gamma, the argument of gamma, is going to be a number lesser than 1. So let's say it is x. So we want x to be positive but lesser than 1. And we have one standard value for gamma of half. So if you're evaluating gamma of half, then this value is equal to square root of pi. Now let us quickly see some simple numericals on evaluation of improper integrals using gamma function. So suppose say I want to evaluate integral from 0 to infinity e raised to negative x over x dx. So we can see that this is going to be integral from 0 to infinity e raised to negative x and x raised to negative 1 dx. Our objective will be to have a power of to have a negative power of e raised to negative x, and also have an algebraic power of x. So in this case, you can see we have got x raised to n minus 1, while here we have got x raised to negative 1. So we wish to write this negative 1 as n minus 1. So if you will simplify this, we get the value of n to be 0. So this means that we can rewrite the integral as integral from 0 to infinity e raised to negative x, x raised to 0 minus 1 dx. And since you can see the value of n in this case is 0, this value is going to be gamma of 0. And as discussed in the values of gamma, we have seen that if n is 0, then gamma of 0 is equal to infinity. So thus we have the answer to be gamma of 0 equal to infinity. So for the second example, we take integral from 0 to infinity e raised to negative x upon x square. So again, we are going to rewrite it in the standard form. So the x square in the denominator comes in the numerator with power negative 2. And again, we are going to write down the power of x as n minus 1. So for this, we will be rewriting it as minus 1 minus 1. And again, you can see the value of n in this case is negative 1. So the value of this improper integral is going to be gamma of negative 1. And we have seen over here that if n is a negative integer, then again gamma of negative n is equal to infinity. Now let's look up at example number 3. So integral from 0 to infinity e raised to negative x, x raised to negative half dx. So we got to rewrite this as integral from 0 to infinity e raised to negative x, and x raised to negative half, we can rewrite it as half minus 1 dx. So as you can see over here, the value of n is 1 by 2. So this is going to be gamma of half. And we have stated that gamma of half is equal to square root of pi. Thus, this value is going to be square root of pi. Next, example number 4, integral from 0 to infinity e raised to negative x into x raised to 5 dx. So for this, we will rewrite it as integral from 0 to infinity e raised to negative x times x raised to 6 minus 1. Here the value of n is 6, so this is going to be gamma of 6. And since it's a natural number, we know that this is going to be pi factorial, which is equal to 120. So these are some very elementary examples in gamma function, and you can see that how simple gamma functions makes these improper integrals which deal with infinities. Now for the next part, we are going to discuss about the various forms of the gamma function, and they again do the same thing. They help us reduce the calculation. So in the second form of gamma function, we are going to see various types. So to begin with, let's talk about type 1. So type 1 is integral of the type 0 to infinity e raised to negative a x power n dx. And the value of this is equal to 1 over n times a raised to 1 by n and gamma of 1 by n. Now over here, I would just like to give you a heads up. So whatever power you see here, in most of the cases, that power is going to be the argument of gamma. So this is type 1. Let us see a couple of examples on this. So example 5. We wish to evaluate the integral from 0 to infinity e raised to negative x power 4 dx. So as you can see over here, we can rewrite this as integral from 0 to infinity e raised to minus 1 times x raised to 4. Thus we have value of a as 1 and we have value of n as 4. So this is going to be using the formula 1 upon n. I'll just take this off. So as you can see, the formula is 1 upon n. N in this case is 4, and then times a raised to 1 by n. So again, a is 1. So 1 raised to 1 by 4, and that's the denominator. And then over here, we are going to take the argument of gamma as 1 by 4. So since 1 by 4, 1 raised to any power is 1. So this entire fraction is simply 1 over 4 times gamma of 1 over 4. Example number 6, integral from 0 to negative infinity e raised to minus 2 x square dx. So again, over here you can see this is very much in the standard form. So we have got the value of a as 2 and n as 2. So using type 1, this is going to be 1 over n. So 1 over n, and in this case is 2, times a, which is 2 raised to 1 by n. And then again, here we are going to have gamma of half. So as you can see, this is 1 over 2, 2 raised to half is square root of 2, and gamma of half is root of pi. So thus this reduces to 1 over 2 square root of pi over 2. Now I'll leave one practice problem, so you can try that. So example number 7 is practice for you. So integral from 0 to infinity e raised to negative x square by 4 dx. So please try, and you can comment the answer in the comment section below. Now let's move on to the next type. So that's type 2. So for type 2, we have integral from 0 to infinity. We have a multiplier x raised to m times e raised to negative a x raised to n dx, and this is evaluated as 1 over n, 1 over a power m plus 1 by n. And then here we have the, again as I told you earlier, whatever is the power of a, that becomes the argument of gamma. So we have gamma of m plus 1 over n. Now type 1 is a special case of type 2. So suppose say I take m as 0. So if you take m as 0, this is going to reduce to integral from 0 to infinity. Now we know that x raised to 0 is going to be 1. So let's not write it. So we get e raised to negative a x raised to n dx. So that's exactly the left hand side of type 1. And for the right side, we are going to have 1 by n. And then over here, a raised to, again you can see that it is m plus 1. So since m is 0, m plus 1 is going to be just simply 1. And here we get 1 by n. And this argument of gamma also reduces to 1 by n, which is the right hand side of type 1. So type 1 is nothing but a special case of type 2. So it will be easier and convenient for you to just remember type 2. And that should help you to do the numericals. Now let us see some numericals on type 2. So example number 8. So we are going to evaluate the integration from 0 to infinity square root of x e raised to negative cube root of x dx. Now the very first thing that you should be doing is you should be removing the radicals. We don't want the integrand to have radicals. We rather want them to be in index form. So let us rewrite. So this is going to be integral from 0 to infinity. Root of x can be written as x raised to half. And then over here we have got e raised to negative cube root of x. So that is going to be negative x raised to 1 by 3 dx. So you can see that we have a power of x and we have a power of e, a negative power of e. So we can relate this with type 2. What is more important for us is to know the values of the constants m, a and n. So if we'll compare it with the formula, we get that m is equal to half, then a is equal to 1 and n is equal to 1 by 3. Here I would just like to give you a heads up that many times students make the mistake of saying that a is equal to negative 1. So please remember that when you do type 1 and type 2, the coefficient of x raised to n by default is supposed to be negative. So here the negative sign is not because of a, it has to be negative. Okay. So coming to the evaluation using type 2, we know that this is going to be 1 over n, and in this case is 1 by 3. Then 1 divided by a raised to m plus 1 by n. So a, since it is 1, m plus 1 is half plus 1 by 1 by 3. And then gamma of m plus 1, that is half plus 1 divided by 1 by 3. So this fraction can be reciprocated and this is going to give us 3. Again over here in the denominator we have a power of 1, and since we know that any power of 1 is always 1, so we can ignore the entire second term and replace it by simply 1. And over here this expression is going to give us 3 by 2 times 3 by 1. So this reduces to 3 times gamma of 9 by 2. Now you see that we have a fraction as the argument of gamma, and we are going to use the last property, or rather the value of n, where we said that if n is a positive fraction. So in that case, what you have to do is you have to observe the argument, and since the argument is greater than 1, we are going to use the recursive values. So this we are going to rewrite it as, now n by 2, if we take 1 less, this is going to be 7 by 2 times gamma of 7 by 2. Again, you see that 7 by 2 is greater than 1. So we are going to again apply the recursive definition. So from 7 by 2, we are going to reduce 1. So this is going to give us 5 by 2 times gamma of 5 by 2. Further, so we have got 3, 7, 5 divided by 2 square. And then again, gamma of 5 by 2, the argument is greater than 1. So we are going to reduce 1 from 5 by 2, and that gives us 3 by 2 times gamma of 3 by 2. Now you don't stop until the argument of gamma is going to be lesser than 1. So again, you can see that we have got gamma of 3 by 2. So this is 3, 7, 5, and we have another 3 here. So we can rewrite this as 3 square. Then power of 2 will become cube. And 3 by 2, if we reduce it by 1, it gives us half, and gamma of half. Now the argument of gamma that we have got is half, which is lesser than 1. So we can stop the recursive definition now and aim for the value. So the final value is going to be 3 square 7 times 5 divided by 2 raised to 4. And as discussed earlier, gamma of half is nothing but square root of pi. So you can use your scientific calculator, since you have the access. You can see what is the value of this expression and write it as that many times root of gamma. So I hope this is quite clear. Now let us see another example of the same type on type 2. So here you can see we want to evaluate the improper integral from 0 to infinity x raised to 1 by 4 e raised to negative square root of x. So we'll begin with calling this integral as I, that is for convenience. So integral from 0 to infinity x raised to 1 by 4. And as discussed earlier, we don't want any radicals here. So we're going to rewrite this as e raised to negative x power half. So comparing it with type 2, let me just show you what type 2 is. So type 2 was integral from 0 to infinity x raised to m e raised to negative a x raised to n dx. And the value of this is 1 over n 1 over a raised to m plus 1 divided by n into gamma of m plus 1 divided by n. So if we compare, we have the value of m as 1 over 4, n as half, and a as 1. So this is going to be in 1 over n, that's 1 over half, and then we have 1 over a, which is 1 in this case, raised to m plus 1. So that's 1 by 4 plus 1 divided by n, which is half. And then we have got gamma of m plus 1, that's 1 by 4 plus 1 divided by half. So this is going to be 2. Again, here in the denominator, we have a power of 1. So we can keep it as 1. And then over here, this is going to be 5 over 4 into 2 over 1. And that gives us 2 times gamma of 5 by 2. And since you see that the argument of gamma is greater than 1, so we are going to use the recursive definition, or rather the recursive property of gamma functions. 1 less in 5 by 2 is 3 by 2. And then we will be getting gamma of 3 by 2. So we will further reduce it. So this will be half. And then here we will get finally gamma of half. So you can see that we can get away with 1, 2. So this is 3 by 2. And then gamma of half is root of pi. So that's the answer for example number 9. Now let's take slightly difficult problem. So we wish to evaluate the integral of x raised to 4 plus 4 e raised to negative 2x square dx. So again, to begin with the solution, we are going to first declare the given integral as I. So let I be integral from 0 to infinity x raised to 4 plus 4 e raised to negative 2x square dx. Now we can split this integral into sum of 2 and rewrite it as integral from 0 to infinity x raised to 4 e raised to negative 2x square dx plus 4 is a constant, we can pull that out of integral 0 to infinity e raised to negative 2x square dx. So as you can see that the integral on the first integral, it is a type 2 integral, while the second integral is a type 1 integral. So, and as discussed earlier, type 1 is nothing but a corollary of type 2. So we can evaluate both the integrals using type 2. So over here, let us first specify the values of a, m and n. So the value of m is 4, a is 2 and n is 2. In this case, we can introduce x raised to 0. So the value of m is 0, a is 2 and n also is 2. And we have the formula right over here. So let's apply that to both the integrals. So we get, therefore, I is equal to 1 over n, which is 1 over 2, and then 1 divided by a, that's 2 raised to m plus 1, which will be 4 plus 1 divided by n, which is 2, and gamma of 4 plus 1 divided by 2. Then plus 4 times. Now the second integral, we have got m as 0, a as 2 and n as 2. So this is going to be 4 times 1 over n, which is 1 over 2, into 1 over a raised to m plus 1. So that's 0 plus 1 divided by n, and then gamma of m plus 1 divided by n. Now we are left to simplify these values. So this is half, and over here we'll get 1 over 2 raised to 5 by 2. This is gamma of 5 by 2 plus 4 times 1 by 2, 2 raised to 1 by 2, and then gamma of half. So you can see that this is going to be 1 over 2 raised to 7 by 2, taking the product of these two. Then we'll be applying the recursive property to gamma of 5 by 2. So that is going to give us the first term as 3 by 2 followed by half followed by gamma half. Over here we have 1 cancellation and then 2 over 2 raised to half. So that's going to be square root of 2, and gamma of half is nothing but square root of 5. So this is 3, and then 2 raised to 7 by 2 into 2 into 2 is going to give us 2 raised to 11 by 2. Gamma of half is 5 plus root of 2 root of 5. So as you can see that we can take root of 5 as common. So if we do that, we will be having 3 divided by, now 2 raised to 11 by 2, we can write it as 2 raised to 5 into root of 2 plus root of 2. So taking the LCM and summing the two fractions that we have, we get 3 plus 2 raised to 5 into root 2 into root 2 divided by 2 raised to 5 root 2 into root of 5. So this is going to be 3 plus 2 raised to 6 divided by 2 raised to 5, and we can write down the two roots, the two radicals together as root of 5 by 2. So 2 raised to 6 is 64, so this is 67 divided by 2 raised to 5 is 32, root of 5 by 2. So that's the answer for the required improper integral using gamma functions. Now let's try another numerical. So it's going to be slightly more trickier. So it goes like this: prove that integral from 0 to infinity e raised to negative x cube square root divided by square root of x dx into integral from 0 to infinity y raised to 4 e raised to negative y raised to 6 dy is equal to pi over 9. So since it's a prove that problem, we do have an advantage because we already know what the expression value is going to be. So let's try to get it done slowly. So let us say that the first integral is I1. So integral from 0 to infinity e raised to negative x cube. Again, we have got a radical. So that radical I'll try and write it as index dx. And for I2, we will be having integral from 0 to infinity y raised to 4 e raised to negative y raised to 6 dy. We are supposed to prove that the product of the integrals I1 and I2 is equal to pi over 9. So first let us try with I1. Now I1 doesn't look very nice in the standard form of type 2. So let us just rewrite. So this is x raised to negative half e raised to negative x cube dx. And since this is type 1 with type 2 with m equal to negative half, a equal to 1 and n equal to 3. So the value of this is going to be 1 over n, which is 1 over 3, then 1 over a raised to some expression, and since we see that the base is 1, the entire index will reduce to 1, and then gamma of m plus 1. So negative half plus 1 is a half divided by n, which is 3. So this simplifies to 1 over 3, and over here we'll be getting 1 over 6. Now since the argument of gamma is lesser than 1, though it's a fraction, but it is lesser than 1, so we cannot perform any recursive properties. So we got to stop the calculation of I1 right here. Now let us look what happens with I2. So again for I2, we have got the integral as 0 to infinity, and it's a nice form, except that there is a change of variable. Instead of x's, we have got y's. So over here, the value of m is 4, the value of a is 1, and the value of n is 6. So using type 2 formula, this is going to be 1 over n, so that's 1 over 6, then 1 over a raised to, again a is 1, so since the base is 1, let's not focus much on the power of 1, and then gamma of m plus 1, so that's going to be 5, 4 plus 1 is 5 divided by n. So this is going to be 1 over 6 times gamma of 5 over 6. So thus we have that I1 times I2 is equal to 1 upon 3 gamma of 1 by 6 into 1 upon 6 times gamma of 5 over 6. So this is actually 1 over 18 gamma of 1 by 6 times gamma of 5 by 6. Now please note that there is no multiplicative property. That means that you cannot go ahead and rewrite this as 1 over 18 times gamma of 5 over 36. So there's no multiplicative property of gamma, so we don't do that. And instead we use a result of gamma functions, which says that if the arguments total up to 1, that is the sum of the arguments is 1, so it is gamma of p times gamma of 1 minus p. This expression is actually nothing but pi over sine of p pi. So in this case, you can see that we have got the two arguments as 1 over 6 and 5 over 6. If you will take their sum, it is going to be 6 over 6, which is 1. So we take help of this property, and by that property we get 1 over 18. Now p, it is p, either you could take 1 over 6 or 5 by 6, it is not going to alter your answer. So this is going to be pi divided by sine of p pi, so that's going to be pi over 6. And we know that pi over 6 is half, so this is going to be pi divided by 1 over 2, which reduces to pi over 9. And that's all the way what we wanted to do. Now let us move on to type 3. So type 3 is a little different because it has got limits from 0 to 1, and in the integrand we have x raised to n times log of x raised to n, and this is evaluated as minus 1 raised to n divided by m plus 1 power n plus 1, and at this moment you should be able to tell me what the argument of gamma is going to be. So the argument of gamma is going to be n plus 1. So a couple of numericals quickly. So example number 12. So let's try and evaluate the integral 0 to 1 x raised to m log of 1 by x raised to n dx. Now, as you see that it is looking like type 3, but then there is slight variation in the argument of log. We need log of x, but over here we have got log of 1 by x. So we got to rework that, and we are going to use the logarithmic properties. So this is integral from 0 to 1 x raised to m, and by logs we know that log of a over b is actually log of a minus log of b. So this is going to be log of 1 minus log of x raised to n dx. So this gives us integral from 0 to 1 x raised to m, and we know that log of 1 is actually 0. So we will be having only negative log of x whole power n dx. So this is integral from 0 to 1 x raised to m. Now for the next part we are going to separate this negative sign, so we can write this as negative 1 raised to n times log of x raised to n dx. And since this factor is a constant factor, it is going to straight away come out of the integral. So integral from 0 to 1, and we have got negative 1 power n as a scalar, x raised to m log of x power n dx. And this looks like type 3. So as per the formula, we have got negative 1 raised to n already outside as the constant, and now applying the formula we are going to have another negative 1 power n divided by m plus 1 raised to n plus 1, and the power n plus 1 is going to be the argument of gamma. So we have got negative 1 power n squared. So, and we know that squares are always positive, so this is going to be only 1. So the final expression is going to be 1 over m plus 1 raised to n plus 1 times gamma of n plus 1. Let's try one more numerical. So example number 13, and in example 13 we wish to evaluate the integral from 0 to 1 x times log of x whole cube dx. So let us separate the powers. So this is going to be x cube log of x whole cube dx, and as you can see we have got the value of m as 3 and n also 3. So in this case m is equal to n is equal to 3, and it is type 3. So the value of this is going to be minus 1 raised to n, which is 3, divided by m plus 1, that's 3 plus 1 raised to n plus 1, that's another 3 plus 1 into gamma of 3 plus 1. So negative 1 raised to 3 is going to be negative 1, divided by, we have 4 raised to 4 into gamma of 4. Now 4 raised to 4 is actually 256, and gamma of 4 is going to be 3 factorial, so that's going to be 6. And we have got slight cancellations over here, so this is going to reduce to negative 3 divided by 128. So that's the answer for problem number 13. Now, as a mean of practice, I want you to evaluate example number 14, and it is evaluate the integral from 0 to 1 dx divided by square root of negative log x. Now, though the problem looks little uncomfortable, but you got to stick to the basic. So firstly, you can see that we have got the limits as 0 to 1. So this tells us that this is type 3 in gamma functions. And secondly, we have got a radical in the denominator. So we are going to firstly move it to the numerator and also get rid of the radical by converting this into index form. So please give it a try, and you can comment the answers in the comment section below. Now let's move on to the final type. The final type is type 4. So type 4 is integral from 0 to infinity x raised to a divided by a raised to x dx. And this is evaluated as 1 over log of a raised to a plus 1 and then here we will have gamma of a plus 1. These types of numericals are very straightforward. So for example, we can evaluate integral from 0 to infinity x cube divided by 3 raised to x dx. And as you can see that the value of a is 3 in this case. So this is going to be 1 over log of 3 raised to 3 plus 1 and then gamma of 3 plus 1. So this is 1 divided by log of 3 raised to 4 to gamma of 4. Now don't apply the property of log and get this power 4 as a multiplier to log of 3. So we can finally simplify this as gamma of 4 is 3 factorial, which is 6. So this is going to be 6 divided by log of 3 raised to 4. Now let's try some mixed examples. So in all, these are the 4 types of gamma functions that you are going to prepare, and of course primarily the definition of gamma functions. So make a list of formulae that we have seen across this video. Now let us deal with some numericals which are of mixed types. So example number 16. So we wish to evaluate the integral from 0 to infinity of 7 power minus 4x square dx. Now you can see that this doesn't look familiar to any of the 4 types that we have seen above, and primarily because there's the exponent is missing. So if you have seen that type 1, type 2 and type 4, they have exponents in them, whereas type 3 did not have exponents, instead it had logarithm, and also at the same time the limits were not 0 to infinity, the limits for that was 0 to 1. So over here we have got limits from 0 to infinity, so we understand that we can probably use type 1, 2 or 4. But to use that, the exponent term is missing, so we are going to introduce the exponent term here. So we begin with let I is equal to integral from 0 to infinity 7 and then power minus 4x square dx. Now we use a simple expression, so any number a, we can rewrite it as e raised to log of a. So we are going to perform that over here. So this is integral from 0 to infinity. Now 7, we can rewrite it as e raised to log of 7 minus 4x square dx. And by the property of log, this exponent of 7 will get multiplied. So we will be getting integral from 0 to infinity e raised to minus 4x square into log of 7 and dx. So you can see now this looks like type 1 or rather type 2, and to write it in that standard form we can say that this is x raised to 0 times e raised to negative, the constant a in this case is log of 7, 4 log 7 into x square dx. So we have m as 0, we have a as 7 and we have n as 2. So as per the formula, the value of this must be 1 over n into 1 over a raised to m plus 1 divided by n into gamma of m plus 1 divided by n. So we get 1 over n, that's half, and then 1 over a, which is 4 log 7 raised to m plus 1. Since m is 0, let's not write it. So 1 divided by n, and then here we have gamma of half. So this is half. Then we can have a split over here. So this is going to be root of 4 into root of log of 7, and gamma of half is nothing but root of 5. So root of 4 is 2, and then we already have a 2 in the denominator. So this is 1 over 4 root of log of 7 times root of 5. So that's going to be the final value for example number 16. Let's try 2 more numericals. So we are on to example number 17, and it says evaluate the integral from 0 to infinity of x square times 7 minus 4x square dx. as you can see that the limits are from 0 to infinity. So this is either type 1, 2 or 4. And also the exponent term is missing. So we are going to introduce the exponent term like we did in example number 16. So x square stays as it is. Now to rewrite this using exponent, we will be writing e raised to log of 7 power minus 4x square dx. And again, by the property of log, this is going to be integral from 0 to infinity x square e raised to minus 4x square times log of 7 dx. And comparing this with the formula, this is the value of m. The value of a is 4 log 7 and the value of n is 2. So this is going to be 1 over n, that's 1 over 2, divide into 1 over a, that is again 4 into log of 7 raised to m plus 1. So m plus 1 is going to be 3 divided by n, that's 2 into gamma of 3 by 2. So this is 1 over 2. Then splitting this up, we will be getting 4 raised to 3 by 2 times log of 7 raised to 3 by 2. And gamma of 3 by 2, we need to write it as half into gamma of half. So this is 1 over 2. Now 4 raised to 3 by 2, it means it is 4 cube, which is 64. And then 64 raised to half is going to be square root of 64, that's 8. And here we are going to have 1 upon log of 7 raised to 3 by 2 into half, and gamma of half is root of 5. So we have 2 8s are 16, 2s is 32. So we'll be having 32 log of 7 raised to 3 by 2, and the numerator is going to be square root of 5. So that's the value of example number 16. Now moving on to the last numerical of this video. Now example number 16 is a very nice numerical as it involves complex as well in it. So to begin with, you can see that the limits of the integral are from 0 to infinity. So we understand that it's going to be either type 1, 2 or 4. But then the entire exponent part is missing. And unlike problem 16 and 17 where we introduced e using logarithms, we are not going to do that. And instead, since we have cos of ax, we know that by Euler's formula, e raised to I theta can be introduced in place of cos theta plus I sin theta. And since the argument of cos is ax, so we are going to work with e raised to I ax is equal to cos of ax plus I times sin of ax. And secondly, we also know that in gamma functions, we don't deal with positive powers of e, we deal with negative powers of e. So we are going to start with e raised to negative ix, which is going to be cos of ax minus I times sin of ax. So let's start with this. So consider e raised to minus I ax, that is equal to cos of ax minus I times sin of ax. Now for the next part, let us consider the integral I, which is integration from 0 to infinity x raised to m minus 1 e raised to negative I ax dx. Now if you will have a look at this integral, then this integral is complex in nature since it has the term I as well, the imaginary unit. Whereas if you will look at the required left side, then it is just the real part of this integral which we have taken. So towards the end, we are going to just consider the real part of this improper integral. Now as you can see that the integral which we have, so we instead of m we have got m minus 1. Instead of a we have got ia, and for n we simply have got a 1. So applying type 2 result, this is going to be 1 over n, that's 1 over n divided by into 1 over a raised to, so that's going to be ia raised to m plus 1 And since m is m minus 1, this is going to be simply m divided by n, that's 1, and gamma of m. So this is going to be 1 over I raised to m, a raised to m, gamma of m. Now have a look at the right side. In the right side, we need cos of m pi by 2. Again, we don't have the imaginary part. So this expression is going to come from this term, I raised to m. So we know that I is actually 0 plus I, and we can say that this is cos of pi by 2 plus I times sine of pi by 2. So therefore we get 1 over I, we are going to write it as cos of pi by 2 plus I times sine of pi by 2 raised to m, and then a raised to m into gamma of m. By de Moivre's theorem, this is going to be cos of m pi by 2 minus I times sine of m pi by 2 into a raised to m, and we can write down gamma m in the numerator. Now you can see slowly we are approaching. So we have got gamma m in the numerator, we have got a raised to m in the denominator. Now we also wish to move the cos of m pi by 2 in the numerator, which here is in the denominator. So we simply are going to move it up, and since this is a complex number, so you have got 1 over z, and 1 over z can be rewritten as z bar, that's the conjugate of z. So we get gamma m a raised to m, and then we having cos of m pi by 2 plus I times sine of m pi by 2. So you can see that we have taken the complex conjugate. So here it was the negative sign, and here we have the positive sign. So now to summarize, what we have is integration from 0 to infinity x raised to m minus 1. Now I'll write down the value of e raised to minus iax, which is cos of ax minus I times sine of ax dx. We have got this as gamma of m divided by a raised to m cos of m pi by 2 plus I times sine of m pi by 2. And lastly, what we are going to do is on the left side we have a complex number. So the real part of this is going to be the integration of x raised to m minus 1 cos of ax, and on the right side the real part is going to be this ratio times cos of m pi by 2. So we'll just simply compare, or by the equality of complex numbers. So comparing real parts on both the sides, we get integration from 0 to infinity x raised to m minus 1 cos of ax dx is equal to gamma of m divided by a raised to m into cos of m pi by 2. And that's what we wanted to prove. So we have seen all whatever could be possible in gamma functions, which is kind of important to you. So we have seen the definition of gamma function. We saw a couple of properties followed by certain standard values of gamma. And then we have seen 4 types of gamma functions, the second form of gamma function, 4 types on it, and solved numericals based on each. And more importantly, towards the end, we saw some numericals which are crucial. They carry higher weightage. So probably 5 marks or 6 marks. So you got to practice all of them. So I hope that this video really helps you in your final minute preparation for your upcoming examination. Thank you so much for watching till the end. If you have any query, any questions, you could put it in the comment box, or you can also drop me an email. And secondly, if you have not yet subscribed to my channel, please subscribe to my channel and also share it with your friends who are preparing for their examination, and gamma function is a module in their curriculum. So wishing you once again all the very best. Thank you so much for watching till the end.